masters, and then once you've done M1 level quantum mechanics, then you're ready to do quantum field theory, again by Mandel. It's about so thick. How many pages? About 350. Okay, so look on quantum field theory is sort of advanced quantum mechanics. That's the M1 level. And M2 level for quantum field theory, where Noether's theorem is very important. I mean, this whole idea of that there's a link, a mapping between symmetry of some kind and the conservation of some physical quantity. So here's the. I don't think I've shown you this before. So this is the textbook I'll use for M2, second year master's level, quantum field theory. It's by Kaku. You may have seen Kaku. He's a well-known popular science commentator on American media. So he's also quite a brilliant theoretical physicist in his own right. He's not just a popularizer. He was one of the pioneers in string theory. So I have quite a few of his books. I'll be using some of them. And here's a PhD level. It's a bit more than quantum field theory, particle physics as well. It's one of the great discoveries of particle physics the last decade or two has been the notion of gauge quantum field theories, or just gauge fields. Don't worry about it. It's just years away. But I'll be using this text as well, I think. So gauge field theories. Also, just in the first few pages of this text, the use of Noether's theorem. So it's sort of basic to the field. Okay. All right. Well, after that rather long-winded preamble, let's start having a look a bit at what we can do at undergrad level in this regard. The idea of symmetry and conservation, so which is symmetry conservation laws. Well, something not too difficult is take the expectation value of some observable A, right? So the average value when you measure A, and does it change with time? Like if you differentiate with respect to time, this quantity, the average value of A, the expectation value of A hat. Okay, so you can rewrite this as this. Okay, and you can rewrite that. Here's your bra operator ket notation. You can rewrite that in terms of your overlap integral. So ddt of integral minus infinity to infinity psi star A hat psi dx. Let's keep it simple. Talk of one-dimensional wave functions. Right. So now let's differentiate this with respect to t. Let's assume that A is not a direct, explicit function of time. It might be implicit, but so we don't differentiate the A, but we do differentiate the psi functions. Okay. In advanced quantum mechanics, there's something called the Schrodinger picture and the Heisenberg picture and the interaction picture. We'll do that in quantum field theory. I'll just give you a taste of it now, because it's here's an example of it. In the Schrodinger picture, it's the wave functions that are functions of time, and the operators are time independent. In the Heisenberg picture, it's the other way around. And in the interaction picture, don't worry about it. It's a bit too advanced. Okay, so differentiate this psi, the integral psi star A psi. Differentiate it. So you get d psi star dt. Okay, you're not differentiating the A, and you get d psi dt here. So you're differentiating this, right? The average value. You're trying to find an expression for this. Okay, Now, we can we can rewrite things a bit, because we have an expression for the general Schrodinger equation. Now, this is not the STI, right? It's not the Schrodinger time independent equation. It's the general equation with the psi function, a function of position and time, x and t. Okay, so here's the general form of the Schrodinger equation. We've seen this before. So h hat psi equals I h bar d psi by dt. And okay, so take the I h bar over the other side. So you now have an expression for d psi by dt, and you can put this here, this 1 over I h bar h hat psi. You can put that here. You can substitute it for here. Okay. Now take this expression and conjugate both sides. Right? So you'll get h bar hat all conjugated equals minus I. If you conjugate I, you get minus I. By definition, that's what conjugate means. Conjugating means, right? So you get minus I h bar d psi star by dt. And take this minus I h bar over the other side. So you now have an expression for d psi star dt here. So it's just minus 1 over I h bar h hat psi all starred. Okay. Now, so you have an expression for d psi by dt. You can put that in here. You have another expression for d psi star by dt. It's this, and you can put that here. So do that. Substitute those two terms into this equation here, the star equation. This star here is just an ID, an identifier. Right? It's got nothing to do with conjugation. Just assume that's obvious. Right? Okay, so you can rewrite this then as this. If you plug in these values, this is just a constant, so that can come outside the integral. And let's see, psi star. So here's your h hat psi all starred. Here it is here, right? A psi. And so d psi by dt is this here. Okay, the I h bar comes outside. Now it's a plus, but you've got a minus, so hence the plus. So d psi by dt is here. So you get you'll get a hat h hat psi. Right. All right. Now let's work on this Let's work on this term here a bit. So writing it out again. So this is just this. Okay. Now it's probably easier when you're dealing with the bracket notation than overlap integral notation. But this you can rewrite. You can rewrite this in the bracket notation this way, right? But by definition. Okay. So you can do that. Okay. So you'll get h bar psi in the bra and a hat psi in the ket. Okay. But H is a Hermitian operator, right? It's the energy operator. So this H here can be put here to the left of the A. So this will become this, and you've moved the H into the ket, and you can do that because H hat is Hermitian. Okay. All right. So for this, you can write it as this. This here becomes this. Now I've skipped a line, but that means that if you differentiate with respect to time, the average of a hat, you will get h hat a hat minus a hat h hat, and with psi's either side. So that h hat a hat minus a hat h hat is the commutator, right, by definition. So you now have an expression for, if you differentiate the average value of A that's equal to 1 over h bar, the expectation value, the average of the commutator of h hat a hat. Right? Now that's for one dimension. We're talking talking here in one dimension. Now you can generalize this kind of logic to 3 dimensions, and you don't even have to have the same size here. You could have like psi and phi, so you can talk about now remember this is the you can look on that as a matrix element of a matrix. Okay? So you can generalize kind of argument to off diagonal, where these two are different functions. So off non-diagonal matrices by using this kind of stuff. All right, now moving on a little bit. What happens if the commutator here is 0? In other words, h and a, or h hat and a hat, commute. In other words, the commutator is 0. Well, if this is 0, if h hat and a hat, if they commute, so the commutator is 0, that implies that this quantity here is conserved. Okay? If you differentiate with respect to time, you get 0. In other words, it does not. As far as time is concerned, it's constant. It's a constant. Differentiated constant is 0. Okay. So if h hat and a hat commute, this quantity, the average of a hat, the expectation of a hat, is conserved. Right? It's constant. Doesn't change. So now, if that's the case, if this commutator is 0, what does that say about a? What's the link between a hat and h hat that makes this commutator 0? Right. So I'll leave you there with a question. Under what circumstances does a hat commute with h hat? What does that say about the nature of a hat? And I'll leave you with that question for the next session and the next board, in fact, because this is the last square of 8 in this whole large, almost 3 square meter board. So until next session.